All right, let's get into one of the weirdest, most beautiful ideas in all of physics, the interference of light. It's this incredible phenomenon where energy doesn't get destroyed, it just gets rearranged. And at the very heart of it is this awesome puzzle. How in the world can you add light to light and somehow end up with total darkness?
Let's just tackle that head on. It feels completely backwards, right? If you turn on one flashlight, the room gets brighter. You turn on a second one, it gets even brighter. So where does this crazy idea of light plus light equals dark even come from?
Well, the key to solving this paradox is to stop thinking about light as just little particles. We have to embrace its true nature as a wave. And the fundamental rule that governs all of this is something called the principle of superposition. So here's the crucial thing to get. When light waves cross paths, they don't crash into each other or bounce off. They actually pass right through each other. And at any single point in space where they overlap, their effects just add up. But what that sum looks like? Well, that depends entirely on how those waves line up. And this diagram shows the two possibilities perfectly. Over on the left, you've got constructive interference. See how a crest meets another crest? They're perfectly aligned, we call that being in phase, and boom, they add up to a way bigger wave. That's our bright spot. But then look at the right. This is destructive interference. A crest meets a trough. They are perfectly out of sync, or out of phase, so when you add them together, you get zero. Nothing. Total darkness. And that is the answer to our puzzle. Okay, so that's the next logical question, isn't it? If the light from your lamp and the light from your window are both made of waves, why aren't we seeing these shimmering interference patterns all over the place? It turns out we're missing a key ingredient. And that missing ingredient has a name: coherence. You see, for us to actually perceive a stable, steady pattern of light and dark, the light sources can't just be doing their own thing. They have to be cooperating, moving in a very specific, very orderly way. And what's so great about this slide is you can actually see the difference. Look at the sunlight up top. It's a total mess, a jumble of different colors and phases all shouting at once. That's incoherent. An LED is a little better, right? It's one color, but the waves are still out of step. To get that stable pattern, you need the perfect order of a coherent source, like the laser at the bottom, where every single wave is marching in perfect lockstep.
So to get this to work, there are three really strict rules. First, the light has to be monochromatic, just one color, one wavelength, so the patterns don't all blur together. Second, the sources have to be coherent, which just means their phase relationship, you know how their crests and troughs line up, stays the same over time. And finally, the waves have got to be traveling at the same speed. If you don't have all three, any patterns that do form just flicker way too fast for our eyes to even notice.
Now, finding two separate light sources in nature that are perfectly coherent is, well, it's pretty much impossible. So physicists came up with this absolutely brilliant engineering hack. They said, fine, if you can't find two, let's just make two from one. And this is the genius solution. You just take a single light source, which is of course perfectly coherent with itself, and you split it. You can do this by dividing its wavefront, which is what happens in the famous double-slit experiment, or you can divide its amplitude, which is what gives you those shimmering colors on soap bubbles. Either way, you create two new sources that are absolutely guaranteed to be in perfect sync with each other. So let's talk about the classic, the one everyone knows, Young's double-slit experiment. Light from one source hits a wall that has two teeny tiny slits in it. Those two slits now act like two brand new, perfectly coherent light sources. Now here's the magic. Depending on where you look on that screen in front, the journey from each slit is a slightly different length. And this difference in the travel distance, that's what we call the path difference.
And honestly, that simple bit of geometry is everything. That path difference, just how much farther one wave has to travel compared to the other, is the only thing that decides whether we're going to see a bright spot or a dark spot on the screen.
And the math behind it is just so beautiful. It's simple. If the path difference is a whole number of wavelengths, 0, 1, 2, 3 wavelengths, the waves arrive perfectly in step, crest to crest. They build each other up, and we get a bright band. But if the path difference is a half number, like half a wavelength or 1.5, then a crest from one wave arrives at the exact same time as a trough from the other. They completely cancel out. That's our destructive interference, and that's our dark band. And this right here, this formula is where it all comes together in such an amazing way. It's more than just an equation. It's like a bridge connecting two different worlds. Think about it. The wavelength of light is measured in nanometers, a scale so tiny it's hard to even imagine. But by measuring things we can see with a ruler, like the distance to the screen, L, and the tiny gap between the slits, D, this formula acts like a giant magnifier. For the first time ever, it lets scientists take something completely invisible and measure it using everyday tools. This was just a massive, game-changing confirmation of the wave theory of light.
Now, while the double-slit experiment gets all the fame, it's really not the only way to do this. The principle itself is what matters, and it turns out there are a few other pretty clever ways to show it in action.
So let's just look at two quick variations. On the left, we've got the Fresnel biprism. It uses a specially shaped prism to bend light from a single source so that it looks like it's coming from two. And on the right, you have Lloyd's mirror, which uses reflection. One light path goes straight to the screen, while the other bounces off a mirror first. And what's so cool about the mirror is that the act of reflecting actually flips the wave upside down. It causes this little phase twist. And the result? The central fringe, the spot that's normally the brightest, is actually dark. How cool is that?
Okay, so let's pull it all together for a final recap. The core ideas, right, are superposition and coherence. They lead to either constructive interference, which gives us light, or destructive interference, which gives us darkness. We saw how Young's double-slit experiment uses a simple path difference to create these amazing patterns, and we even checked out a couple of other ways to do it, like with a biprism or Lloyd's mirror.
And that kind of leaves us with one final big question to chew on. This whole thing is about taking an invisible property of light, its wavelength, and using a really clever setup to make it visible to our own eyes. Makes you wonder, doesn't it? What other hidden invisible properties of our universe are just waiting out there for us to discover, if only we can figure out the right way to look?